Good afternoon. We resume our lecture again today. This is continuing the lecture series on Six Sigma. The topics for today are going to be design for manufacturing, which is also called DFM, and reliability. This would be the first half of this introduction to FMEA, and the second half is going to be basically an explanation of FMEA process itself. That's what we'll be doing. So we start out with the title slide, which is DFM and reliability. That's what we'll be doing today. Design for manufacturing. This is a particular approach to design products so that they become easier to manufacture. In fact, the coverage would be starting out with what is DFM, why use DFM, why use this particular approach, what is the process like, how you approach it, what are the tools used in DFM, and what are the methods that you utilize. And then, of course, I'll provide you with an overview, and I'll give you a comparison of DFM versus other methods for approaching design, which does not consider manufacturability, as an example. And of course, I'll give you some references, so you'll be able to go on and study more about DFM. What exactly is design for manufacturing? If you look at a product, almost any product, ultimately, you've got to remember that it's got to be manufactured through some manufacturing system. If it is designed in a way that is not conducive to easy manufacturing, the cost is going to be high, perhaps the quality will be affected, perhaps the handling would be affected, and so on and so forth. So we've got to make sure that the design itself keeps this mission in mind, that eventually I've got to produce this product in a manufacturing outfit. This being the goal, certain special approaches have to be taken to make sure that you can manufacture product that you've designed. Why do you do DFM? Of course, a couple of benefits are there right away. You lower your cost, you shorten the development time, you come up with a faster time to reach that startup build, which is like when you go into commercial production. You'll have lower assembly cost and lower testing costs also, and of course, you'll end up with high quality. These are the advantages in approaching the task using the DFM approach. There are many tools, many processes, and so on and so forth. How do they all fit together? A couple of things we got to remember is, it's a fairly straightforward method in that it comes along with some guidelines. If you follow the guidelines, you'll be designing your components correctly. You'll make sure that the assembly is right. You make sure that the assembly actually goes through some processing steps, which are also easy to execute. These are some of the things that will be there to try to make sure that what you produce can be done conveniently at a quick pace of time, and of course it would cost you less. These are the goals of DFM. Why do DFM? In fact, if you look at DFM, and if you look at the engineering changes that are required many times after the design has been launched, which means after it has been commercialized, if I've not kept in mind DFM, if I've not kept in mind this end step, which is manufacturing in mind, if I've not done that, and if I just do a design and I throw it over the wall and it lands up in the manufacturing shop, there are going to be a lot of problems. If you look at engineering changes, many times a lot of things are discovered when you actually get into manufacturing. A lot of problems are discovered when you get into manufacturing. That's something we'd like to avoid, we'd like to minimize. I've got a little bar chart here. It actually shows the cost of a change when you do it at the design stage versus when you do it at the testing stage, testing the prototype, for example, or when you do some changes in the design at the tool building stage, or when production begins, you start doing some fiddling around with the design itself. That's going to be very expensive. If you look at the impact, of DFM, DFM actually is rather, it's something that really saves you money right up front. There is a trace here of committed cost, and the committed cost begins to rise as you go toward production. The committed cost, that's the commitment made by the company to go ahead and produce something. If you do it at the design stage, the actual cost incurred is quite low. Then at testing, again, the cost incurred is quite low. But as you complete your tool building and you get into manufacturing, most of your costs are actually incurred. If you could take care of this early on, in fact, if you could reduce your commitment, it turns out it's far better to approach the total task in the DFM way than having to do it when, for example, when production begins. You look at two approaches to optimize the design. One is, of course, the traditional approach, which means you let things go till they reach manufacturing. And when the project is launched, then you really try to optimize the design, optimize the parts, optimize materials, optimize manufacturing methods, and so on. For that's going to be rather late. It's also going to cost you more. Instead, if you start optimizing a little ahead of time, which is like, let's say on some units of time, 20 weeks ahead of time, then maybe 10 weeks ahead of time, if you put some commitments there, the cost that you'll be incurring, the extra cost that you'll be incurring due to all these changes that are required now, because these were not addressed when you're doing your real design, those are going to be much less if you go the optimized route as opposed to going and doing it the conventional way. What is the manufacturing scenario today? I'll show you a couple of examples. I'll show one or two examples where you'll see that manufacturing has become far more challenging, far more complex. It's very difficult to coordinate a lot of these things because our supplies have become global and there is global competition. We have to compete now with the best all over the world, wherever they are from. They could be from Japan, Europe, India, Mexico, Malaysia, anywhere. Manufacturing can be done anywhere. Parts can be made anywhere. And of course, they are all brought together in whoever is doing the final assembly. This is certainly true for cars. It's also true for home appliances, true for electronic parts, and so on and so forth. Even airplanes, parts are made in different places and they're shipped over. So someone makes the engine, someone makes the elevator, someone makes the fuselage, someone makes the wings, and so on and so forth. It is all brought together in one place, and then the assembly is done finally. Quality requirements have also become global. ISO 9000, of course, now Six Sigma, everyone is talking Six Sigma. Product cycles have become much shorter. That is where manufacturing is today. The rate of change is, of course, also increasing. That's also something there. If you look at costs, costs have been decreasing because of the learning effect and because of competition. Take an example of a disk drive. Take a look at a disk drive, which is just your standard DVD or CD drive. There are components which are made in different places. For example, there are certain wafers required. Those are made in probably China or Ireland. And some sliders are required to assemble this particular product, and those might be made in China. Certain parts are made in Mexico, certain parts are made in Taiwan and Philippines, and so on and so forth. And of course, Singapore also might be doing some manufacturing, and so on and so forth. Assembly might be done in a location that is quite different where the parts were made. The electronic card might be being made in Malaysia, and it's all brought together into one place where the assembly is done, which in some case could be Singapore or Hungary or Philippines or Thailand or somewhere there. Now, there's a lot of coordination to be done here. There's a lot of coordination. That's the global picture today, because you want to minimize the overall cost. This has a couple of things for us to keep in mind. Once the supply chains have become long, you've got to do quality assurance when you've got supplies coming from faraway places. You've got to take special effort to make sure your supplies are in place. The conventional approach to product design, how was it done? Well, we went through development cycle when we did a lot of changes and so on and so forth, and there were non-standard parts used in the conventional way, and these usually had long lead times because they were not non-standard parts. They all had to be made each of a kind. Quality also was something that I just mentioned to you. It was the design was thrown over the wall, and what was hoped was that the manufacturer will catch it and he will then go on with his detailing of the manufacturing process and so on and so forth. Now, of course, things have changed. Manufacturers are very closely involved with the designers, and designers make a lot of trips to the manufacturing shop to try to understand what are the processes, what are the choice of materials, machining conditions, assembly conditions, and so on and so forth. All those things are brought into play when someone puts together a design today. That's like today's design. If you look at cost, because of unique designs and specialized parts, costs were higher traditionally. And of course, equipment and tooling, if these were not done right, and they were generally not done right in the conventional product design approach, the whole product ended up costing a lot more. What is the new approach? A couple of things have changed. One, of course, the conceptual design is where you begin to design. And then you'd be doing some optimization. Perhaps you might be doing experiments, perhaps you might be building prototypes, perhaps you might be doing Taguchi methods and so on. You'd be building tools, and these tools also have to be built in such a way that the final assembly is easier. Launch will be done by ramping and then shipping and delivering and so on. So this is the product launch. The product team, these are the guys who are given the charge of bringing the product right out of the final gate. You know, their charge is start from design and take it all the way to the finish line. This is their job. So now we've got product teams that take charge of this. That's like something that is also where DFM comes in. Design for manufacturing. You want to make sure that you're designing something that can be manufactured easily. What are some of the considerations in DFM? There are obviously the environmental considerations. That is definitely very much there. You got to worry about pollution. You got to worry about green manufacturing conditions. You got to make sure you do a certain amount of recycling, shock, vibration, temperature. These have to be looked at. They are environmental factors that you got to look at. You got to also look at suppliers and their capabilities, and perhaps you'll have some partnerships with your part suppliers and your major assemblers, for example, those who produce these sub-assemblies. Then customers also play a major part here, because you got to make sure you understand their requirements. And this is something that is, you get techniques like QFD, you get techniques like customization, you got techniques like the Kano approach to categorize customer satisfaction, customer requirements, and so on and so forth. You've got some special test requirements. These are sometimes required by certain customers. These also have to be kept in mind once you're going to design for manufacturing. And of course, processing and tooling. The processes, they have to have their own, they have their constraints of cycle time, and that has to be optimized again. Quality has to be looked after. Ease of assembly, ease of testing, rework, shipping and handling, all these things they have to be done, right? So today, design for manufacturing would require actually for you to go into all of these things. And none of these things can be left out, and you hope to get a good design done. That's just not possible anymore. What are some of the tools? Well, just to give you a few acronyms. Design for assembly. This is to make sure that the assembly can be done easily. It does not become a strain. After you got the parts made and the sub-assembly is made, the assembly itself does not become a bottleneck. FMEA, this is a technique that is utilized, and I'll be spending some more time. I'll be spending a lot more time a little later to tell you about FMEA. This is failure mode and effect analysis. A design or a process or a product can fail many different ways. And before you go into commercial production or before you commission the final product, you've got to make sure you've done FMEA. You've tried to predict in what different ways, in what different modes can a product fail. You also have to make sure when you're doing this, you look at the effect, and you look at a couple of things. One, the first thing you look at is how likely is it going to fail? What is the likelihood of a particular mode of failure? In what different ways can it fail? That is mode. Then you got the likelihood of failure. Then you got to look at the impact. Look at the impact of that failure. And then you've got something called detectability. All these things have to be there. And this is what you've got to do. If you've got for example, if you've designed a disk drive as an example, you have to predict through your analysis, and this would be the FMEA analysis. With that, you'll have to predict in what different ways can it stop functioning or give trouble to the user. These have to be projected in terms of their likelihood, their impact, their detectability, and of course, later on you'll have some control actions or some rectification actions, which will make sure that the impact, the eventual impact is low, or probably the likelihood is almost next to nil. You also have Taguchi method. That's also another design for manufacturing tools, and we discussed Taguchi methods early on in this course. That's like one method by which you can create robust designs. Your design should be such that the final performance is on target and it's not affected too much by the environment. That is something that Dr. Taguchi was to come up with. He was able to come up with this special method where he used experiments, and we've seen many experiments in this lecture early on. And there are special types of experiments which are multi-factor experiments, and these are called orthogonal array experiments. And these are the experiments that are utilized to try to make sure you find the optimum settings for the different design parameters when you're trying to design something. The same thing can be done for a process also, and you can come up with a robust design for the process or a robust design for the product itself. That is something. Value engineering is also something that, for example, I've listed the companies there. Value engineering is capitalized by Hewlett-Packard as an example. They are the ones who say whatever you put together, it must give some value to the final user. It should not be there only as bells and whistles. So you got to make sure whatever you are adding, if I've put a strange clip on this, it must have some value, otherwise I don't need it. If I've got something fancy inside this pen, I've got to make sure it has added some value to it. Maybe life of the ink or something. It's got to do something useful. Otherwise, just a waste. And this is something you'd like to avoid. And to be able to do that, what you do is once you've got your basic design done, you try to do value engineering. And with that, you can reduce cost. You can make it more reliable. You can make it more functional and so on and so forth. And basically what you're doing is whatever resources you're putting into the final product itself, it's all going to add to value, some value that will be of some help, or either it's going to reduce cost or it's going to probably raise its value as far as the final user is concerned. That's something to be done. QFD is also a tool, quality function deployment. We've discussed this before. What it really does is it looks at customer requirements before design specs are drawn up. It looks at customer requirements as we discussed in trying to do our QFD exercises before. I think we looked at, this was a dry cleaning shop, what all features should be there in the services that they provide, and what should be their target values, what should be the target values of these different services that this shop will provide, this dry cleaning shop will provide. We of course want to make sure we maximize customer satisfaction, at the same time we minimize cost. These are some of the things that we'll have to do. So whatever the customer is looking for, I've got to capture that by capturing the voice of the customer through this QFD process. Then of course, if there are similar parts to be made, I've got to take advantage of something called group technology. So if there are a lot of turning to be done of different dimensions, what we'll have to keep in mind is that these turnings are grouped together and they're done at one workstation. Because otherwise what will happen, you'll have dissimilar processes all being thrown at the workstation, and there will be a lot of switchovers, a lot of changes, a lot of setup costs incurred additionally, and this is something you'd like to minimize, and this is why you'd like to go into something called group technology. IBM exploited this very, very well in doing their computer manufacturing. Then of course you've got the standard quality assurance methods and cost management methods. You have SPC, and now of course we've got Six Sigma. In addition, of course, we've got TQM and TQC. These also help out with DFM, Design for Manufacturing, when you're trying to do this. Let's again take a look at that disk drive, and if you take a closer look at the screen, you'll be able to read a few things. For example, the assembly is to be done in a top-down manner, so that no adjustments would be required, no hidden features would be required. The test direction of axis also is going to be from the top. These are guidelines given to the design for manufacturing specialist. Sub-assemblies are to be done in order to reduce total handling. Holes have to be large enough to make sure the axis is there, and of course you've got to make sure all the fixtures and so on and so forth, they come together properly. I've got to look at the parts. We've got to make sure they are easy to fabricate. They are standard parts to the extent possible. For example, one screw type used throughout the assembly. Parts are self-guiding. If you put them there, you put a screw in a place, it goes right in exactly where the thread is supposed to be. That's like something that's part of a good design, and it really helps out in manufacturing. Avoid tangled with the use of fixtures. This happens a lot when you've got wire harnesses and so on and so forth. You've got to make sure things are easy to fit, things are easy to, kind of isolate and so on and so forth. That is like something that is done a lot when you're trying to, for example, put together a motorcycle. At the design stage itself, they try to figure out how is it going to be put together. And then they try to make sure it's going to be easy for the person who's going to be doing this. And the same thing would apply for electronic device such as this drive there. And we've got some other considerations, like in this particular case, symmetry, die-cast material, and the bottom rails for conveyor. You've got to make sure that the product is able to ride the conveyor. That's like something that happens a lot. If you look at a bottle, for example, right at the bottom of the bottle, you'll find some grooves, and those grooves are of no use to the user, the person who's going to be putting some liquid in this bottle. But this is a great aid when it's going through that filling line, and the bottle has to turn or it has to stay secure so that the cap can go on. For that, we need those little studs there. That's something that is always done. It's done in a way that makes manufacturing easier. Design for assembly, I've got a list of guidelines here, and I'll let you read this at your own time, so you can actually stop your play of the video, and you can actually read off some of these things. You can also, of course, you can find them in design books. They are there. I just want to make sure that you keep some of these things in mind before you finalize your design. Because eventually the design is to be done such that the final assembly can be done conveniently. This is something that we require. Then, of course, you move slowly into FMEA. FMEA is really failure mode and effect analysis. What is this approach? You try to predict failures, and you try to look at first of all, the different modes by which it can fail. What are the different ways a disk drive could fail, for example? Then you try to identify what would be the impact if that particular thing failed, and what is the likelihood for it. With this, you try to find out the seriousness of the problem itself, and you work out something that I'm going to tell you later about, called the RPN, or the risk priority number. This helps you prioritize the different actions. The different actions can be prioritized if you do this RPN calculation. With the RPN calculation, you end up with getting kind of a sorted situation when the items which are likely to fail, highly likely to fail, for example, and that will have a big impact, that will end up with a high RPN. And these are the ones that you've got to address first before you go into any of the other details. This is what is done very systematically using the FMEA worksheet. And I'm going to be showing this to you. As we go into this, we'll be showing this to you. Just the overview of the method itself. I have an example in the next page when I'm going to be showing you how exactly a disk drive is put through this FMEA process. You'll see certain cells, you'll see certain columns, you'll see certain entries there. And those are done eventually to make sure that for every mode of failure that you've identified, you go down to the root cause and you try to make sure you either reduce the likelihood of that failure or you reduce the impact of it. And you do that by addressing all those items that end up with a high RPN, a high risk priority number. Those are the ones you'll attack first. You try to reduce either the likelihood or the impact. Then you go on with the others that have the lower RPN. That's what you'd be doing. Here's an example. The same disk drive, it could fail in many different ways. So the parts that can actually cause problems is the cable alignment, or the heat sink, or soldering, or the holder. These could cause problems. In what different ways could it cause problems? The flux may not be clean. There may be some bent component there. Some touch-up may be required in certain places. Flashes may be there because of injection molding and so on. And with that, you end up with a high likelihood of failure taking place as far as cable alignment is concerned. Then, of course, the next one is the heat sink. That may give you also trouble. And the other ones tend to be lower. So now here I've got a priority sorted out for me. The total weight is 100. 42 is the weight given to the problems associated with the cable alignment. Heat sink picks up 36, which is like 1/3 of the problems are expected to go there. And the others are about 10–12%, so they're not much of a thing. So we should be giving the highest priority in terms of tackling it to this issue about the cable alignment not being proper. There are certain guidelines which are also used and certain tools are used. Guidelines, of course, are there to try to make sure you got cost minimum, you got to have minimum effort in doing your design, and certainly finally the final manufacturing. You'd be using the management team approach. These are some of the advantages directly coming out of the guidelines that you've got. And the disadvantages that sometimes you got to have exceptions which are not covered by the guidelines. This is like if you're doing DFM, you might be using guidelines, and these would be the things that you should be doing in addition to just following the guidelines. Then you've got Taguchi methods, and the Taguchi method actually is a very systematic method. These are some of the advantages, and it narrows down the possibilities of things going wrong because you already got a robust design. And what are the disadvantages of the Taguchi method? First of all, management may not really understand what you're trying to do, and it will require special effort from the designer to be able to do this. So these are going to be some organizational challenges if you're trying to go the Taguchi way. As far as FMEA is concerned, it's a very systematic method. So this is also an approach that you could use in DFM. It will help you prioritize corrective actions. It will also provide guidance. What are some of the problems? You got to make sure you manage this whole effort properly. and make sure that you worry about the ease of assembly. This is something you got to be able to do when you're trying to do FMEA. And here's a little chart that gives you a comparison of these different approaches to try to these different approaches or these different activities which are utilized to try to make sure you do your design for manufacturing. You got the product concept, you'll be simplifying some of the concepts. You got to look at the requirements of the processes that you need, and you got functional requirements, which is like where the actual action is going to be. That also will be there. So what is the summary of DFM? If we summarize this very quickly, is design considering manufacturing, because my eventual goal is to be able to manufacture that product there. What are some of the advantages? We will end up with shorter development time, lower cost, higher quality. These are some of the things coming out of this. And there will be fewer engineering changes, which will not be there if you do not go the DFM route. The approach itself is integrated, and of course, this is not designed in a vacuum. You've got constant dialogue going with the manufacturing unit. So you've got to make sure that you maintain this so that problems are not found when manufacturing gets into the act. Problems are design problems are not discovered when you get into the act there. Tools and methods, these are actually pretty standard now, and I've gone through some of those tools and methods there. Those are the ones you'd be using, and please remember, FMEA is a very important tool, and we'll be using FMEA as we go into this. I've provided you with some references, which again, if you take your time, you'd be able to probably find most of these in your library. I'll move on now to this great area called reliability. And reliability basically is the ability of a product or a service, in fact, to perform as expected over a period of time. So this is not quality exactly when I unpack the item. It's actually not the thing that is like the quality of it or the performance as of day zero. It's the performance of the product over the life of the product, over the useful life of the product itself. And this is, of course, something that is greatly impacted by design. You can make a very big impact on reliability if you design things right. Let's take a look at some of these things. First of all, what exactly is reliability? It's, like I said, it's the ability of the product to perform as expected over time. Reliability is also defined as a probability that the product will perform over a specified period of time under specified operating conditions satisfactorily. This is something, if these features are there, that product is, I would call it a reliable product there. Quality is a term that's also sometimes it's confused with reliability. You got to make sure customer really, quality is a term that is basically a customer perception term. And reliability is basically related to performance. Reliability looks at the chance of preventing failure to satisfy the customer's requirement. So there could be errors in design that could lead to reliability questions. There could be flaws introduced by the manufacturing process. The environment could impact and reduce the reliability of a particular product. Product could be misused. That would also reduce its reliability. And many times, because we do not completely understand the customer's wants and needs, I could end up with an unreliable product. How is reliability presented by professionals? Well, they say you take almost any product. You take something as simple as a CD, which is something that we'll be hopefully using without any trouble at all. We just open the pack and start using it. If you look at 1,000 of these, a few of those will have problems, and these are the ones that die early. These are called the infant mortality products. And this is a small period of time. A few products die there, and these are generally because of manufacturing problems. And those sneak in, they get into the packaged stuff, and you end up with with these products when you take them home, and so on and so forth. So there is cure for this, and that is done by doing this burn-in before the product is shipped. Now so the failure rate is pretty high early on, and this is the infant mortality stage. Then you've got the service range, and this is exactly this is a region of operation for the product that has got low failure rate. And this is exactly why we buy a product. We buy a product to be able to use it. Like, for example, this pen I bought, I hope to be able to use it for 2 weeks without any trouble at all, because its life is expected to be a couple of weeks when I start using it. I use it maybe about 3-4 hours a day. It should last me something like a couple of weeks. That's like expected. That's going to be this time there. That's the useful lifetime. Then, of course, things wear out. For example, the ink may be gone, or the tip itself may become a little fuzzy and so on and so forth, so the tip may not be as sharp as it was when I bought the pen, when I opened it up. This is the wear out period. This is the wear out period. Failure rates increase here, as you noticed here. This curve, by the way, looks like a bathtub, so it's actually called the bathtub curve. The job of reliability engineering is to try to prevent failures, is to try to do whatever you can to try to reduce failures. This is the mission for this. And this is to be done beyond the infant mortality stage. We understand that infant mortality is because of manufacturing defects, just as you are getting products straight off the line. Not many products actually will have these problems, just a few percent, perhaps, even that. But it's the period of use over which I've got to make sure that failures are rather few and next to zero if possible. Two types of failures could be there: reliability failure, that is like after some time of use, and functional failure takes place almost immediately. As soon as you take it out of the box, there may be a functional failure. Like you bought a fan, or you bought a computer or a laptop or something, and it does not function, within a few days of using it, it does not seem to function right. That's a functional failure. A reliability failure is after you've used it for 6 months or a year, then it begins to act up. That means the product is not reliable. This again is shown by that bathtub curve, and there is something called inherent reliability. Inherent reliability can be predicted by looking at the design of the product. There are some approaches by which you can predict the inherent reliability of the product itself. And of course, there is something called achieved reliability, which is like in the actual site of use, actual location of use. There, for example, if I start using a laptop, or if I start using a particular portable disk drive, for example, what is going to be the history of its breakdown, or even something as mundane as a bicycle, or perhaps a scooter, or a vehicle, for example. There will be a designed reliability condition, which will be the inherent reliability of the product, and of course there is going to be the achieved reliability. And of course we want to make sure that the achieved reliability is at least as good as the inherent reliability. This is something we'd like to be able to do, because then customer satisfaction is going to go up. How do we convey this notion of reliability? It's done always by number of failures over time. So this is called the failure rate, which I've called lambda here. Notice here the Greek letter lambda. This tells you the mean failure rate, which is the number of failures per unit time, which could be per year, and in some cases it could be per month, and hopefully it will be over a decade, or for large construction projects it could be over perhaps 100 years. How many failures would take place over 100 years? That's like something you'd like to keep your eye on. So failure rate is one great indicator of how good or bad reliability is. Some of the measures are there: mean time to failure and mean time between failures. These are also measures that are used. And getting back again to the bathtub curve again, I've got early failure, which is when lambda is high. Then lambda becomes quite low in the intrinsic failure period. This is like the service period. And then of course lambda begins to rise, the rate of failure begins to rise when you come down to what we call the wear out period. And if you look at the cumulative time, the curve tends to flatten out in the when there is not much change in reliability over the service period. Initially there is some decay and reliability begins to improve, and then of course as the product begins to wear out, again reliability begins to change. What we would be interested for most part in the service phase of the product itself. That is the part where this slope is smallest, and therefore the number of failures per unit time is also going to be smallest. This is something we would like to be able to do. As far as average failure rate is concerned, you span the full spectrum, the full life cycle of the product, and that will be starting at, in this case, starting at 0 hours, going all the way to 5,000 hours when everything completely failed. And that slope will give you the overall average failure rate. Mind you, the failure rate in true situation would be higher in the beginning and also higher toward the end. And in between, you'd actually enjoy a failure rate that's going to be smaller than the overall average. The same thing can be said again if you look at the bathtub curve. There is the early failure period phase, then there is the useful failure rate, useful life, then of course the wear out failure. These are the three phases in almost any product. What your goal should be, you should design a product in such a way that the useful life is as long as possible and the failure rate during that useful life is as low as possible. If you do these two things, you're doing good design. You're doing good reliability engineering. Of course, you've got to use some strategies right early on to make sure that not many manufacturing processes are good, so that there are not too many early deaths. And also you've got a replacement, a maintenance policy in place, so that this decay toward the end, it does not become catastrophic. This is also something you've got to take care of. But for most part, reliability focuses on the useful life of the product. We'll take a look at, as we go into this, measuring reliability. How do you do it? One great way is to look at the probability of operating to an agreed level of performance over the period of time. This is like RT. RT is the reliability, that's the probability. And unreliability, of course, is the probability of failing to operate over that period of time that you'd like it to be functioning. You'd like the thing to be functioning. And if you add these two, RT and FT, that's obviously equal to 1. RT is the probability of surviving, and F is the probability of failing before the time period T is over. And that's got to add up to 1 for sure. In the service life period, generally speaking, your reliability stays the same, and lambda becomes a constant there, and there the failure time distribution turns out to be something we call exponential. You notice here, I've shown you the exponential formula there. That is the density that actually controls the distribution of failure times in what we call the service phase of the period itself, and the cumulative distribution is shown there. Failure rate is lambda. Lambda is constant in the service period there. And the reliability function itself, which is the length of time the device operates before it fails, that has this exponential distribution. This is how it is. Now, as far as the tail ends are concerned, remember the two ends of the bathtub curve, they tend to rise. There are special distributions that are applied at the beginning, which is like when the early deaths are there, and also when the wear out deaths are there. These distributions are different. These statistical distributions of failure times are different from that flat exponential part. These two ends, they are governed by what we call the Weibull distribution, and the Weibull distribution has its own peculiar formula. It also belongs to the exponential family. It's a very, very useful distribution. It's a distribution that can be specialized to a curve that is coming down. It can be specialized to a case when the curve is flat, the density, probability density is flat. It also can be used to show a rising or a deteriorating situation. All these three scenarios can be modeled by the Weibull distribution. So the Weibull distribution is a very, very popular distribution in reliability engineering. I've shown you the formulas, I show you the density, and also I show the average times, and of course I show you the computed values of the reliabilities. Those I show, and I show you the mean time to I show you the mean time to failure distribution, and also I show you the rate of failure. Those are all shown here. If you've got real data, if you've got live testing data, which means if you, let's say you start with a total of 2,000 products, these could be light bulbs, and you'd like to establish this bathtub curve for it, what you really have to do is get these 2,000 lamps and at some point in time light them up. Put some power into them and light them up. And then just wait till the first one fails, the second one fails, the third one fails, and so on and so forth, and keep account of this as time goes along. So let's say you are doing this by an hour, and you're doing this by an hour, and you're keeping track of how many failed. So in the first period, 650 of those lamps went out, and the next 350 went out, then the third 210 went out, fourth 166 went out, fifth 131 went out, and so on and so forth. And toward the end again, it begins to rise. Now this, if you can actually see, this is kind of like your bathtub curve. It's kind of like that bathtub curve there. Initially you've got coming down, then it becomes somewhat flat, then it begins to rise again. You are able to see this bathtub curve business there. And then I show here the different columns. If you come toward the end of the table here, you'll end up finding the reliability, and you'll notice there reliability tends to become flat and low at a certain point in time. This is something that you can see very, very easily. You're able to see that as you look through these numbers there, you'll be able to see that. And FT is of course the cumulative probability that an item would have failed by this time. And of course, when 2,000 hours are up, everything dies, all the components are gone, all the lamps are gone. So this mode of collecting data by doing live testing is really a big tool to try to establish reliability. Some products that you produce in large quantities, if you could do live testing on them, you'd be able to come up with, for example, warranty period estimates and so on and so forth. That's something you should be able to do this. If you look at this pictorially, I have these red dots here, and they tend to show you the failure rate. The failure rate is shown here. And the green line, the green dots, they connect the reliability. So you notice here the reliability begins to come down and down and down. Of course, reliability, in the end, nothing survives, so that thing is gone there. So these two show how failure rate changes. It was somewhat high in the beginning, then it became low, then it began to rise again. This is something you should be able to figure out by looking at the live testing data. And of course, the other thing is you should be able to predict reliability also with this. Most of the time, the period in which you have interest is the middle period, which is like the flatness of the bathtub curve. That you'd like to be able to do. The mean time to failure for non-repairable items, those are shown by the formula which is here. T1 is the time period over which it is working. TD1 is the downtime for that. Then you replace that with another item, which is item number 2, and it operates for T2 period of time, length of time, and TD2 is the period for which it is done. Now these are non-repairable. That means I'm not doing repair, but I'm procuring the other item there. If I do this, I'm able to end up with something that I call mean time to failure, which is like the sum of these TIs divided by the total number of failures taking place. And mean failure rate would turn out to be just basically the inverse of this. That will turn out to be mean failure rate. And then mean downtime, that would be like the period over which the things have been down because I'm procuring a new product there. This is a non-repairable product. If I've got repairable items there, repairable item basically means that I'm repairing and putting back the same item again and again and again. And the formulas are given here. Again, I've got mean time between failures. The formula is shown here. And the failure rate, that also is shown here. The mean failure rate is also shown here. These are metrics which are used quite often in doing reliability engineering. Then you've got something called availability, which is like the period of time over which a product is available. And you can actually utilize this, and that is MTBF divided by MTBM. That is the time between maintenance plus the mean downtime. These are together. That covers you the total covers the total time. Then of course you've got MTBF, mean time between failure. This is actually your availability time. Then you've got something called inherent availability, which is like MTBF divided by MTBF plus MTTR. MTTR is mean time to repair, because here we are repairing and putting the system back again. A0 and A0 and A, these become our availability figures, and these basically should be pretty high. For example, if you've got a generator, if you've got a standby generator that produces electricity when power is out, you've got to make sure the availability is right there. Same thing would go for almost anything that comes along as a backup. You've got to make sure the availability is right up there. Design for reliability, this is something you've got to keep in mind, and this is influenced a lot by element selection, the components that you buy, component that you put together, the environment, the complexity of the product itself, and any kind of redundancy that you'd like to be able to do. Let's see how this is brought together in a system. The reliability of a system really depends on how it is configured. So that configuration could be either in series, you got the components all laid out in series. If any of those components fails, the whole system comes down. So if any component fails and the whole system comes down, most likely the components are connected in series. That's like the picture that I show here. Here the reliability of the system, which is the probability that the system is going to survive, it's going to be up and running for the period of time over which you are doing the evaluation, is going to be the product of every one of them surviving for that period of time. So reliability of system is equal to R1 times R2 times R3 and so on and forth. Any of these R's, of course, are what we call 1 minus the probability of failure. If I do the same thing there, let me show you how it works out. Let's say the components themselves have failure time distributions which are exponential. Then the reliability, it turns out, will be 1 minus Ft. And let me just write a little formula here for you. Ft is lambda E minus lambda T, when lambda and T are greater than 0. This is the distribution of failure time. If that is the distribution of failure time, then the probability that the item will fail before time T is up, this is 1 minus E minus lambda T. This is the probability that a failure will take place before time T is up. Then therefore, what is the probability that the product will survive? It is basically 1 minus Ft. This is the probability of, this is called reliability. This is the probability that the product is going to fail beyond T, beyond time T. And this is exactly what we want. We want this to be as high as possible. This is my reliability. This number is reliability. And if a system is in series, then this reliability turns out to be this R system. This turns out to be e to the power minus, I've got lambda 1 plus lambda 2 plus and so on and so forth, plus lambda n multiplied by t. And this is going to be for a system that has got components which are like this. They're connected in a series. And the full system is, this is lambda 1. Failure rate here is lambda 1, lambda 2, lambda 3, and so on and so forth, this lambda n. If this is the picture, the reliability of this total system is going to be this. This is a fairly simple, easy to remember formula when every component must survive in order for the system to survive. And the system is the full system. This total thing is the full system. This is what you see on the screen there. I've got I to O connected, provided all of them are surviving. The picture is slightly different when you've got things in parallel. Then, of course, any one of the components, if they're in parallel, any one of the components surviving would actually mean that you've got a reliable system. Any one of the components surviving, any of the components surviving would mean that you've got a reliable system there. And there, of course, the failure would take place if all of them fail. Therefore, the chance that the system will fail is the first one fails and the second one fails and the third one fails and so on. So here it's going to be a slightly different formula. Look at the probability here. System probability is equal to 1 minus the chance that the first one failed and the second one failed and the third one failed and so on and forth all the way. If I convert this into our exponential formula, it gives us this expression. It gives us an expression which is like this. This gives us the system reliability. So it actually says the more components I have in parallel, the higher will be my system reliability when systems are in parallel. And this is why we provide redundancy. Whenever we provide redundancy in a system, we make sure that systems, the additional components, they come in parallel. And they are really at standby situation, or they might even be functional, but they are still in standby situation. So if the main component breaks, the second one is going to come kick in and is going to give me the reliability that I want. If I've got a complicated system, such as I've got a mixture of some parallel and some series components, if that is what a configuration is like, the rule of thumb is convert everything, convert all the parallel items, calculate compute the total reliability of all the parallel systems, replace that total parallel system by one component now, which is equivalent of the parallel system there. Then put the rest of them in series. And this is exactly what has been done here. These two components, they are in parallel. So they have been replaced by the C prime. C prime is the equivalent of this guy there. And the rest of them, they are in series. And therefore, I've got now my probability of the total thing coming like this. And this is what it would be like. Reliability management. How do you end up managing reliability? Start with your customer performance. Start with customer performance. Determine the importance of the economic factor that might be, like, for example, downtime, what it is going to cost you. Define the environment and the condition of products used. Select components, designs, and vendors such that you really meet your reliability criteria and the cost criteria. Both of those you got to be able to take a look at. Determine the reliability requirements of machines and equipment. This is something you got to be able to do if you are trying to manage reliability. And analyze field reliability. You take a look at actual performance and just see, is that good enough for me? Configuration is design management. Basically, certain things are done, which is like established procedures. This is something you should be able to do. And I've listed them out here. And I've listed out some more things. Other design issues also are there. For example, maintainability. That's like a big, huge issue in design. If I put a system together, I should be able to repair it. I should be able to reach into the parts. I should be able to do it. So if you're trying to change an oil filter, for example, you should not have to hike the car. You should be able to do it from the tap. You should be able to do it, reach there and do it. Many times what is happening now is you've got jumbled up wires and tubes and pipes and everything else, and it does not really become easy to maintain. And certainly modern cars, they've really gone overboard this way. And the older cars, I must admit, they were very easy. I mean, most of the parts were easy to access. Maybe their performance was not as good, but at least the layout was such that you could do it quite easily. This is something you got to keep in mind. Why consider maintainability? If you don't do that, the total cost of downtime is going to go up. And if you are not able to maintain the car, then you'll be doing less preventive maintenance, and it's going to raise the risk of failure. Corrective maintenance is actually done in response. After the failure has taken place, then you do corrective maintenance. This is something you should not have to get into. Then there's some other tool called FTA. FTA is fault tree analysis. If something fails, take a look at its component and see how they are configured together. So if the bulb fails, as an example, if the bulb fails, if there is no light, it could be because of no electricity, or the glass is broken, or filament is broken, or vacuum leak is there. That's why the bulb has failed. There is no light. Then you look at filament. Why did the filament break? Maybe there were impurities, or there was a vibration. There was some vibration that caused it. No electricity. What could have caused this? Power plant had a failure, power line had a failure, or the connector got corroded. Many times this happens when you got a vehicle and you've not really looked at the battery cables for a long time, the battery electrodes for a long time, and they may begin to corrode because the acid is there and stuff, and you may not be washing it, cleaning it, and so on. So that will lead to that. Power line failure. What could have caused it? A tree could have fallen on the line, or perhaps wind probably led to that. So this will lead to what we call the FTA. A car brake, for example, it would not work because of any of these things. Brake performance is marginal, or brake does not release, or the brake does not work. Any of these things could have been caused by any of these components there. So this is what we call a fault tree. A fault tree is a tree built of various things that could go wrong, and either they kind of work in parallel or they work in series. So you could have an OR situation, or you could have an AND situation, which is like something will not be functional if all the components are not working. That means all the components means none of them is working. And then if the system fails, of course you've got one particular situation. And if any one coming down brings the whole system down, that means things are in series, you've got to approach it differently. So this is where fault trees become very, very handy. What I'd like to be able to suggest is that you take a look at your bicycle and you try to draw an FTA diagram using that. This is an exercise you should try to complete before you move on to the next class. So please, think of the bicycle, try to construct your FTA from it. And so for some reason, I wanted to rush to the class, but I couldn't do it because my bicycle stopped functioning. Something went wrong, and you start with different ways it could fail, different modes by which it could fail, and then see what could have caused it. Either I had a puncture, or the chain broke, or something jammed, and so on and so forth, or perhaps the ball bearings have gone or something. You've got to figure that out. So try to do an FTA before you go further. And we'll continue with our discussion of FMEA in the following lecture. See you in a little while. Thank you.